In this chapter, we are going to study the major physical properties of fluids. Before we can analyze pipe flow, pumps, turbines, flow over cars, aircraft, or biological fluids, we first need to understand what properties control fluid behavior. The main topics are density, specific gravity, vapor pressure, cavitation, energy, compressibility, speed of sound, viscosity, surface tension, and capillary effects. The big idea is this: a fluid's properties determine how it responds to pressure, temperature, motion, surfaces, and external forces. Here we introduce the continuum assumption. In reality, matter is made of atoms and molecules. In gases, especially, the molecules can be widely spaced. But in most engineering problems, we do not track individual molecules. Instead, we treat the fluid as a continuous medium. That means properties like pressure, density, temperature, and velocity are assumed to vary smoothly from point to point. This is called continuum assumption. The key condition is shown at the bottom of the slide. The characteristic length of the system must be larger than the molecular spacing. So, for example, air flowing around a car or water flowing through a pipe can usually be treated as continuum flow. We do not need molecular level modeling for those cases. This assumption is what allows us to use calculus and differential equations in fluid mechanics. This slide introduces four very important fluid properties: density, specific volume, specific gravity, and specific weight. First, the density is defined as mass divided by volume. Rho is equal to m by v. Here rho is density, m is mass, v is volume. The SI unit is kilogram per meter cube. For specific volume, small v is equal to capital V by m, where capital V is the meter cube and mass is the kilogram. Basically, it is the inverse of density. There is a worked out example which shows how they are related to each other. Now, the other quantity is specific gravity, that compares density of a substance to the density of water. It is denoted by Sg. So Sg is equal to rho of any fluid under consideration divided by rho of water at 4 degrees Celsius. This is a ratio, so it has no units. If specific gravity is greater than 1, the substance is denser than water. If it is less than 1, it is less dense than water. Depending upon that, we can determine if the substance is going to float or submerge in water. The last quantity to address is specific weight. Specific weight is the weight per unit volume. It is denoted using different notations, but in this textbook it is notated using gamma underscript S, which is equal to rho times G. Specific gravity table. So this table gives specific gravity values for several substances. Water has a specific gravity of 1, which means that's the reference value. Seawater is slightly above 1 because it contains salt. Gasoline and ethyl alcohol are below 1, so they are lighter than water. Mercury and gold have very high specific gravity values. That means same volume of mercury or gold contains much more mass than same volume of water. The practical interpretation is if Sg is greater than 1, it sinks in water. If specific gravity is less than 1, it floats in water. This is the reason why wood floats in water, but metals and such type of substances will fall into the water. Now we move to vapor pressure and cavitation. The first term is saturation temperature. This you might have already learned in thermodynamics, but this is a recall. This is the temperature at which a pure substance changes phase at a given pressure. For example, water boils at about 100 degrees Celsius when the pressure is 1 atmosphere. The second term is saturation pressure. Saturation pressure is the pressure at which a pure substance changes phase at a given temperature. Third term is vapor pressure, written as P subscript V. Vapor pressure is the pressure exerted by vapor molecules when the vapor is in equilibrium with liquid at a given temperature. For pure substance at equilibrium, PV is equal to Psat. So, vapor pressure and saturation pressure represent the same physical condition when the liquid and vapor are in equilibrium. The slide also introduces partial pressure. For a gas mixture, the total pressure is the sum of partial pressures of individual gases. For moisture, we can write P atmosphere is equal to P dry air plus water vapor. This is important because air is not just dry air, it contains water vapor, and that water vapor contributes to the total atmospheric pressure. Now, this slide shows vapor pressure using water molecules at the liquid vapor interface. Some of the molecules at the surface of the liquid have high energy to escape into the vapor phase. At equilibrium, the vapor molecules exert a pressure on the liquid surface, and that pressure is the vapor pressure. The table shows saturation pressure of water at different temperatures. The key trend is as the temperature goes up, the vapor pressure also goes up. At low temperatures, water has low vapor pressure. At high temperatures, water has high vapor pressure. At 100 degrees Celsius, the saturation pressure of water is about 101.3 kilopascal, which is approximately 1 atmosphere. That is why water boils at 100 degrees Celsius under atmospheric pressure. In this slide, we will visit a new concept called cavitation. Cavitation occurs when the local pressure in a liquid drops below the liquid's vapor pressure. We can state cavitation condition as P local is less than P vapor. When this happens, vapor bubbles form inside the liquid. These bubbles are called cavitation bubbles. But the most damaging part occurs later. When these bubbles move into high pressure region, they collapse violently. That collapse can generate very large local pressure waves. This can damage impeller blades, turbine blades, propellers, valves, pumps, etc. So the practical warning is this: in liquid flow systems, we must make sure that pressure does not fall too low. If it drops below the vapor pressure, cavitation can occur. Cavitation can also cause noise, vibration, erosion, and serious performance loss. Now, this slide contains several important relationship and equations between different quantities. The first one is enthalpy. Enthalpy is, and majority of these you have already covered it in thermodynamics. Again, this is a recap of what we have learned. Enthalpy is defined as the combination of internal energy and the flow work, so it is H is equal to U plus PV. Since specific volume is equal to 1 by rho, we can also write this in H is equal to U plus P by rho, where H is enthalpy per unit mass, U is internal energy per unit mass, P is the pressure, and rho is the density. And the total energy of the flowing fluid is defined as H plus KE plus PE, which is basically flow energy plus internal energy plus kinetic energy and potential energy. And in terms of specific heats, we can relate internal energy and enthalpy using the expressions du is equal to Cv dt and dH is equal to Cp dt. It can be written in differential forms as well. and that is given in the subsequent equations. This slide introduces compressibility using bulk modulus. The coefficient of compressibility or bulk modulus is written as K is equal to minus V dP by dV at constant temperature, which is also equal to rho times dP by d rho at constant temperature. The negative sign appears because when pressure increases, volume decreases. So the sign correction makes the bulk modulus positive. For small changes, the equation will become K is equal to approximately delta P by delta rho by rho, or equivalently minus delta P by delta V by delta V by B. This tells us how much pressure change is needed to cause a fractional change in volume or density. A large K means the fluid is difficult to compress. Liquids usually have very large bulk modulus, so they are often treated as incompressible. For a truly incompressible substance, the volume is constant, so K is approximately equal to infinity. The slide shows K equal to 0 for coefficient of compressibility depending on how the term is defined. But the physical idea is this: the incompressible fluid does not change volume when pressure changes. Next, we will take a look into water hammer. The water hammer is a practical example when where liquid compressibility matters. Imagine water flowing through a pipe. If a valve closes suddenly, the moving water cannot stop instantly. The liquid near the valve becomes locally compressed, and this creates a pressure wave. That pressure wave travels through the pipe, reflects from the bends and valves, and causes the pipe to vibrate. This creates the familiar banging sound. The basic sequence is normal flow, abrupt stop, pressure wave formulation, wave reflection, vibration, and possible damage. Even though water is usually treated as incompressible, water hammer reminds us that liquid do compress slightly, especially during rapid pressure changes. Water hammer can damage pipes, valves, fittings, and equipment. This is why piping systems may need slow closing valves, surge tanks, or water hammer arresters. So a typical water hammer arrestor is shown here. And this slide shows two water hammer protection devices. The first one is called a large surge tower. So what it does is, when you have a very large pipelines as shown in here, when you're closing the pipeline, because of water hammer, it can damage the system. So this surge tower can accommodate the excess pressure by filling it with the excess water, and that can reduce the water hammer effect. So this is for the large scale, but in household devices, you can use these type of water hammer arresters. Even though these devices look very different in size, both are solving the same fluid mechanics problem. They protect the system by giving pressure wave somewhere to go instead of allowing it to damage the pipe network. Now, if you apply the compressibility to ideal gases, this is how it turns out to be. An ideal gas equation is given as P is equal to rho times RT. P is the pressure, rho is the density, R is the gas constant, and T is the absolute temperature. At constant temperature, we can differentiate pressure with respect to density. So dou P by dou rho at constant temperature will become P by rho. So an ideal gas under isothermal conditions, the bulk modulus is equal to absolute pressure. This means the pressure as the pressure increases, the gas becomes harder to compress. Now another expression for this is delta rho by rho is equal to delta P by P. That means the percentage increase in density is equal to the percentage increase in pressure for an ideal gas when the temperature is constant. It also defines isothermal compressibility where alpha is equal to 1 over K. And with that definition, we can substitute the values and we will get alpha is equal to 1 by V times dou V by dou P at constant temperature. This simply is the inverse of bulk modulus. Now we will look into a coefficient of volume expansion. Coefficient of volume expansion is written as beta is equal to 1 by V times dou V by dou T at constant pressure. It can be also written in terms of density. Beta is equal to minus 1 by rho times dou rho by dou T at constant pressure. Again, the reason for negative sign is when temperature increases, volume usually increases but the density decreases. For small changes, the approximate relationship is beta is equal to delta V by delta T, which is equal to delta rho by delta T. This coefficient tells us how much fluid expands when temperature increases at constant pressure. A large beta means the fluid volume changes significantly with temperature. For an ideal gas, beta is equal to 1 over T, where T must be in absolute temperature. T must be absolute temperature in Kelvin. This property is important in thermal expansion, natural convection, buoyancy, and atmospheric flow. Now consider an aircraft which is flying near to the speed of sound. The visible cloud around the aircraft is caused by condensation of water vapor in the air. Around the aircraft, the pressure and temperature can drop suddenly. If the temperature drops enough, the water vapor condenses into tiny droplets, forming a visible cloud. This does not mean the aircraft is literally breaking a wall. The so-called sound barrier is not a physical barrier. It's a compressible flow effect when pressure wave, density changes, and temperature changes becomes very important. So this shows like how important is compressibility effect for high speed gas flow. Speed of the sound and Mach number. The speed of the sound is speed at which very small pressure disturbance travel through a medium. The equation for any fluid is c square is equal to dou P by dou rho at constant entropy. The subscript S means the process is isentropic, which means no entropy change. The equation can be also written as C is equal to root of K over rho or root of K RT. Here K is the specific heat ratio, R is the gas constant, T is the absolute temperature. Again, we will define something called Mach number. Mach number is the ratio between actual speed of the object and the speed of the sound in that fluid. So Mach number is denoted using MA. MA is equal to V by C, where V is the actual speed and C is the speed of the sound in that fluid. For MA less than 1, the flow is called as subsonic. For MA is equal to 1, the flow is sonic. MA greater than 1, the flow is supersonic. And if ma is very large, then it is called hypersonic. So Mach number is a measure of, especially in terms of, in the case of aircraft, it's not just the measure of how fast the aircraft is moving, but it is about how fast it is moving compared to the local speed of the sound in that medium. Now here we will introduce a term called viscosity. Viscosity is a property that represents internal resistance of a fluid to motion or fluidity. A fluid with high viscosity resists motion strongly. For example, honey, syrup, and heavy oil. A fluid with low viscosity moves more easily. Water and air are common examples. Viscosity is also related to drag force. Drag force is a force which is exerted by the flowing fluid on a body. For example, air flowing over a bird creates drag. The water flowing over the shark also creates the drag. And same does by the air against the aircraft. The physical source of viscosity is internal friction between fluid layers. When the neighboring layers move at different speeds, the viscosity resists that relative motion. So, viscosity is one of the key properties determining how much frictional resistance exists in a fluid flow. So, this slide shows fluid between two parallel plates. The bottom plate is fixed and the top plate moves at the constant velocity v. U is equal to v, which means u means x-axis direction velocity, v is the magnitude of it, so it is moving along the x-axis at a constant velocity v. And we will introduce the no slip condition, which means the fluid next to the wall will not be moving, but it will be attaching to the wall. So in that case, the fluid layer at the bottommost plate will remain as it is, and the fluid layer near to the top wall will move along with it. So the velocity profile of that is as shown in here. If you are looking at fluid on the top, it is having higher velocity, and as you go down, the velocity is smaller. If the flow is laminar, the velocity profile between the plate is linear, which means u of y is equal to y by L times v, where u of y means the variation of velocity along the y-axis. X directional velocity along the y-axis, that's what u of y means. And this L is the distance between the plates, and y is the distance from the bottom plate at any location. The velocity gradient is defined as du by dy and can be found as v by L. For Newtonian fluid, shear stress is proportional to the velocity gradient. So that means tau is directly proportional to du by dy, or we can write dB by dt, where dB is the small differential angle, or the angular velocity is what dB by dt means. And if you remove the proportionality, we have to introduce a constant, and that constant is called the coefficient of viscosity, or we can also say it as the dynamic viscosity. This equation, tau is equal to mu times du by dy, is called as Newton's law of viscosity. Now the shear force area is A, and that if you multiply by the tau, we will get shear force. And now if you substitute the expression for shear stress from here, you will get mu A times du by dy. So that is the expression for shear force in viscous flow. The unit of dynamic viscosity is pascals seconds. Another terminology we have to introduce is called kinematic viscosity. Kinematic viscosity is defined as nu is equal to mu by rho, where nu is equal to kinematic viscosity, mu is dynamic viscosity, and rho is density. Dynamic viscosity tells us fluid's resistance to shear deformation. Kinematic viscosity tells about the ratio of viscous effects to density effect. It is especially useful in fluid flow and Reynolds number calculations. The unit of kinematic viscosity is meter square per second. And it also has a unit of Stoke. An example on the right shows the effect of pressure on air. At 20 degrees Celsius and 1 atmosphere, air has a certain dynamic viscosity and kinematic viscosity. At same temperature but at a higher pressure, 4 atmosphere, the dynamic viscosity stays nearly the same but the kinematic viscosity decreases because the density of the air increases when the pressure increases. If mu stays almost constant and rho increases, then nu, which is the kinematic viscosity, will decrease. Now, effect of temperature on viscosity. For liquids, viscosity decreases as temperature increases. And at the same time, for gases, it will increase when you increase the temperature. This happens because gas viscosity is mainly caused by molecular collisions and momentum transfer. At higher temperature, gas molecules move faster and collide more often. That's the reason why we will experience higher viscosity for gases at high temperature. The next term is surface tension. Surface tension occurs because molecules at the surface of a liquid experience an imbalance of molecular forces. The molecule deep inside the liquid is pulled in all directions by the neighboring molecules, but at a molecule at the surface has fewer neighboring liquid molecules above it. So the force is not balanced correctly. It will experience a net pull to the bottom and towards the sides compared to a molecule in the bulk. This makes the surface behave like a stretched elastic film. The equation shown here is sigma s is equal to F by 2 times B. This is demonstrated for the example shown on the right side. If you have a fluid film and if you try to move that particular movable wire to the right side with the force of F, and the dimension of that fluid film is B, then the stress is equal to, or the tension is equal to F by B, which is basically Newton per meter. It's not the stress, it is the surface tension. The factor of 2 appears because liquid film has two surfaces, front and back. The work done to stretch the film is equal to W is equal to force times distance, which is F times delta x. So F is equal to 2 times B times sigma x times delta x, which is equal to sigma s times delta area. Now this shows how surface tension creates pressure differences across curved surfaces. For a droplet or an air bubble, the pressure inside is higher than the pressure outside. For a droplet or an air bubble, delta P is equal to Pi minus Po, which is equal to 2 times sigma x by r. Here Pi is the inside pressure, Po is the outside pressure, sigma S is the surface tension, and R is the radius. This tells us that small droplets have larger pressure differences. And for the case of soap bubble, the equation becomes delta P is equal to Pi minus Po, which is equal to 4 sigma x by R. The factor 4 instead of 2 is because the soap bubble have two surfaces, an inner surface and an outer surface. Now the main idea is the curved surface create pressure jumps and pressure difference becomes larger when the radius becomes smaller. This concept is important in bubbles, sprays, aerosols, foams, boiling and cavitation. Now we will look into another important effect called capillary effect. Capillary action occurs when the surface tension interacts with solid wall, such as inside of a thin glass tube. Water wets the glass because adhesive forces between water and the glass are stronger than cohesive forces within the water. So water rises in a narrow glass tube. Mercury does not wet the glass because cohesive forces within the mercury are stronger than adhesive forces between mercury and glass. So mercury falls in the tube. The capillary rise equation is H is equal to 2 times surface tension divided by density, gravity, radius, that radius of the glass tube, and the contact angle, cosine of the contact angle. This equation tells us several things. If the surface tension increases, capillary rise increases. If the density increases, capillary rise decreases. Tube radius increases, capillary rise decreases. That's the reason why to demonstrate capillary effect, people usually choose a slender tube, not a bigger pipe. The contact angle determines whether the liquid rises or falls. For water, you can see this is the meniscus, and because of the unbalanced surface tension, it will pull the liquid upward. For mercury, the meniscus is the other way. That's why the mercury goes down instead of going up in the capillary tube. Now, a summary on this particular chapter. The main message is the fluid behavior depends strongly on fluid properties. Density tells us how much mass exists in a given volume. Specific gravity compares substance to water. Vapor pressure tells us a liquid may begin to vaporize. Cavitation occurs when pressure drops below vapor pressure. Compressibility tells us how much a fluid volume changes with pressure. Speed of sound describes how fast pressure waves travel. Viscosity measures the resistance to deformation of fluid. Surface tension controls droplets, bubbles, and capillary rise. Many of these properties appear directly in equations, so when we solve fluid mechanics problems later, we are not just plugging in numbers. We are using physical properties to describe how the fluid actually behaves.